Google's Willow chip, redefining reality with quantum supremacy. Introduction, a quantum leap into the unknown. In December 2024, Google unveiled its Willow quantum chip, a technological marvel that has sent shockwaves through the scientific community and beyond. This 105-qubit quantum processor didn't just break records, it obliterated them, solving a computational problem in under 5 minutes that would take the world's fastest supercomputers 10 septillion years to crack. That's a 1 followed by 25 zeros, an incomprehensible timescale that underscores Willow's unprecedented power. But Willow's achievement goes beyond raw speed. It has reignited debates about the very nature of reality, with some scientists speculating that its capabilities might hint at computations occurring across parallel universes. This isn't science fiction. It's the cutting edge of quantum mechanics. In this exploration, we'll dive deep into what Willow achieved, why the multiverse hypothesis is part of the conversation, the skepticism surrounding Google's claims, and the transformative potential of quantum computing in 2025 and beyond. Prepare to have your mind stretched as we unravel the implications of a technology that might be rewriting the rules of the universe. The quantum breakthrough, what Google's Willow achieved understanding. Quantum computing basics. To grasp the significance of Willow, we need to start with the fundamentals. Classical computers, like the ones powering your phone or laptop, operate using bits, binary units that represent either a 0 or a 1. These bits process information sequentially, which, while reliable, limits their ability to handle exponentially complex problems. Quantum computers, however, operate on a radically different principle, using quantum bits or qubits. Qubits harness two key phenomena of quantum mechanics: superposition and entanglement. Superposition allows qubits to exist in multiple states simultaneously, both 0 and 1 or any combination thereof, enabling quantum computers to explore countless possibilities at once. Entanglement, meanwhile, creates a deep connection between qubits, such that the state of one qubit can instantly influence another, no matter the distance between them. This synergy allows quantum computers to perform computations at scales unimaginable to classical systems. Google's Willow chip, with its 105 qubits, is a pinnacle of this technology. Pushing the boundaries of what's computationally possible, Willow's monumental achievement. Willow's defining moment came when it tackled a random distribution benchmark, a task designed to showcase quantum computing's unique strengths. This benchmark required generating outputs from highly complex entangled quantum patterns, a problem so intricate that classical supercomputers would need 10 septillion years to solve it. Willow completed the task in just under 5 minutes. This wasn't just a speed improvement, it was a demonstration of quantum supremacy, the point at which a quantum computer outperforms even the most advanced classical systems on a specific task. Google first claimed quantum supremacy in 2019 with its 53-qubit Sycamore processor, which solved a similar problem in 200 seconds, a task they estimated would take classical computers 10,000 years. Critics, including IBM, argued that optimized classical algorithms could reduce that time to days, casting doubt on the claim. Willow, however, is a different beast. Its 105 qubits represent an exponential leap in power, as each additional qubit doubles the system's computational capacity. This makes Willow orders of magnitude more capable than its predecessors, silencing many earlier criticisms. Advancements in error correction. One of quantum computing's biggest hurdles is fragility. Qubits are notoriously sensitive, with even minor environmental disturbances, temperature fluctuations, electromagnetic noise, or cosmic rays, causing errors that disrupt computations. Google's breakthrough with Willow includes advanced error correction techniques, a critical step toward making quantum systems reliable. By implementing sophisticated algorithms and hardware improvements, Willow maintains coherence longer, reducing error rates significantly. This stability is a game changer, bringing practical quantum computing closer to reality. Implications for the future. While Willow's random distribution benchmark is a theoretical exercise, its implications are profound. Quantum computers of this caliber could revolutionize fields like cryptography, where they might crack encryption protocols that secure global communications, while also enabling quantum-based, unbreakable encryption. In drug discovery, quantum simulations could model molecular interactions at unprecedented scales, accelerating the development of life-saving treatments. Climate modeling could benefit from quantum optimization, enabling more accurate predictions and solutions for mitigating global warming. Even artificial intelligence stands to gain, as quantum algorithms could enhance machine learning models, making them faster and more efficient. In 2025, as industries race to adopt emerging technologies, Willow's achievement signals that quantum computing is no longer a distant dream, but a tangible force. Governments, tech giants, and startups are investing billions, $24 billion globally in 2024 alone, according to recent industry reports, underscoring the urgency to harness quantum power. Willow is a milestone, a proof of concept that quantum systems can tackle problems beyond the reach of classical computing, setting the stage for a transformative decade. The multiverse connection. Are parallel universes at play? The multiverse hypothesis. Willow's staggering performance has sparked a provocative question. Could quantum computers be tapping into parallel universes? This idea stems from the multiverse hypothesis, a concept rooted in quantum mechanics and popularized by physicist David Deutsch's many worlds interpretation, NWI. To understand this, we need to revisit superposition. In quantum mechanics, particles and qubits exist in multiple states simultaneously until measured, at which point they collapse into a single state. The mainstream Copenhagen interpretation views this collapse as a random selection from a probability wave, with other possibilities vanishing. The MWI, however, proposes something far more radical. Every possible outcome of a quantum event actually occurs, but in separate, parallel universes. For example, if a qubit in superposition represents both 0 and 1, measuring it yields 0 in our universe, while another universe sees it as 1. Scale this to a quantum computer with 105 qubits, and the number of parallel universes involved becomes astronomical, potentially infinite. Deutsch argues that quantum computers like Willow might perform their lightning-fast calculations by distributing computational tasks across these parallel realities, with the final answer emerging in our universe. Willow and the multiverse. Willow's ability to solve a problem in minutes that would take classical systems 10 septillion years lends credence to this idea. Its 105 qubits, operating in superposition, explore an immense number of computational pathways simultaneously. If the MWI is correct, each pathway could correspond to a different universe, with billions of Willows working in parallel across the multiverse to produce the final result. This would explain quantum computing's almost supernatural speed, as it leverages resources beyond our single reality. In 2025, the multiverse hypothesis is gaining traction, fueled by advances in quantum technology and cosmology. Recent experiments, such as those at CERN exploring quantum entanglement, have hinted at phenomena that challenge conventional physics. Posts on X from leading physicists suggest growing openness to the MWI, with some calling Willow's performance the first practical evidence of multiversal computation. While speculative, this idea is electrifying the scientific community, as it suggests quantum computers could offer insights into the structure of reality itself. The Copenhagen counter-argument. Not everyone is convinced. The Copenhagen interpretation, still the dominant framework in quantum mechanics, argues that superposition is merely a mathematical tool for describing probabilities. When a quantum system is measured, its wave function collapses into one state, with no need for parallel universes. Critics of the MWI, like physicist Sabine Hossenfelder, argue that the multiverse is an untestable hypothesis akin to philosophy rather than science. From this perspective, Willow's speed is a product of cleverly manipulated quantum probabilities, not interdimensional teamwork. The debate remains unresolved, but Willow's achievement has brought it to the forefront. In 2025, quantum computing conferences, like the upcoming Q2B 2025 in Silicon Valley, are dedicating sessions to the MWI, reflecting its growing relevance. Whether Willow is harnessing parallel worlds or simply pushing the limits of probability, its performance challenges our understanding of computation and reality. Skepticism and limitations. Tempering the hype. The practicality problem. As groundbreaking as Willow is, it's not without critics. One major point of contention is the nature of its achievement. The random distribution benchmark, while a stunning display of quantum power, is a contrived problem with no immediate real-world applications. Sabine Hossenfelder, in a recent blog post, likened it to building a hyperloop to travel between 2 points in a lab. It's impressive, but its utility is limited for now. Practical quantum computing requires algorithms that solve tangible problems, like optimizing supply chains or simulating chemical reactions, and Willow's benchmark doesn't directly address these. Scalability challenges. Another hurdle is scalability. Willow's 105 qubits are a remarkable feat, but practical quantum computers will need millions of qubits to tackle real-world problems reliably. Each additional qubit increases complexity exponentially, not just in hardware, but in maintaining coherence. While Google's error correction advancements are promising, they're not yet sufficient for large-scale systems. In 2025, competitors like IBM with its 133-qubit Heron processor and startups like Rigetti are also making strides, but the industry consensus is that fault-tolerant quantum computing is still a decade away. Energy and cost. Concerns: quantum computers are also resource-intensive. Maintaining qubits at near absolute zero temperatures requires sophisticated cryogenic systems, which consume significant energy. A 2024 report from the International Energy Agency estimated that quantum data centers could demand as much power as small cities by 2030. Additionally, the cost of building and maintaining quantum systems is astronomical. Willow's development likely cost Google hundreds of millions. For quantum computing to become mainstream, these barriers must be addressed. Competitive landscape: Google isn't alone in the quantum race. IBM, Microsoft, and China's Baidu are advancing rapidly, with Baidu recently announcing a 72-qubit processor in January 2025. Ex-posts from industry insiders suggest that China's quantum program is particularly aggressive, with potential applications in military cryptography. This global competition is driving innovation, but also raising questions about Willow's long-term dominance. Will Google maintain its lead, or will a rival leapfrog with a more practical system? The road ahead. Skeptics aren't dismissing Willow, they're urging caution. Quantum computing is a marathon, not a sprint, and each milestone, even theoretical ones, builds toward a future where these machines could transform society. In 2025, optimism is high, with venture capital pouring into quantum startups at a record pace $1.2 billion in Q1 alone per pitch book. The potential rewards: faster drug discovery, unbreakable encryption, optimized energy grids, are too significant to ignore. Willow is a stepping stone, proving that quantum supremacy is real and paving the way for practical applications. The broader impact: quantum computing. In 2025 and beyond, industry transformation. In 2025, quantum computing is transitioning from research labs to industry applications. Financial institutions like JP Chase are exploring quantum algorithms for portfolio optimization, potentially saving billions in inefficiencies. Pharmaceutical companies, such as Merck, are investing in quantum simulations to accelerate drug development, with early trials showing promise for cancer therapies. Even logistics giants like FedEx are eyeing quantum optimization for supply chain management, a market projected to reach $10 billion by 2030, according to McKinsey. Geopolitical implications. Quantum computing is also a geopolitical flashpoint. The ability to break classical encryption could destabilize global security, prompting nations to invest heavily in quantum-safe cryptography. The US, China, and the EU are racing to set standards, with NIST expected to finalize its post-quantum cryptography framework in late 2025. Ex-posts from policy analysts highlight concerns about a quantum arms race, with implications for everything from military communications to financial systems. Ethical and societal questions. As quantum computing matures, ethical questions are emerging. Who will control access to this power? Could quantum systems exacerbate inequality if only mega corporations and governments can afford them? And if the multiverse hypothesis proves true, what philosophical implications arise from computing across realities? These questions are sparking debates at forums like the World Economic Forum, where quantum ethics is a growing focus. The human element beyond technology. Willow's story is about human ingenuity. The researchers at Google's Quantum AI Lab, many of whom have spent decades in obscurity, are now global celebrities. Their work exemplifies the power of interdisciplinary collaboration, blending physics, computer science, and engineering. In 2025, quantum computing is inspiring a new generation of scientists, with universities like MIT and Oxford reporting record enrollment in quantum-related programs. Conclusion: a glimpse of the quantum future. Google's Willow chip is more than a technological triumph. It's a window into a future where the impossible becomes routine. By solving a problem in minutes that would take classical computers 10 septillion years, Willow has cemented quantum supremacy as a reality. Its advancements in error correction bring practical quantum computing closer, while its mind-bending performance fuels speculation about parallel universes. Skeptics remind us that challenges remain: scalability, practicality, and cost. But the trajectory is clear. Quantum computing is poised to reshape our world. In 2025, we stand at the cusp of a quantum revolution. From cryptography to climate modeling, the applications are vast, and the stakes are high. Whether Willow is tapping into the multiverse or simply mastering probabilities, it's pushing the boundaries of what we believe is possible. As we move forward, one thing is certain. The age of quantum computing has begun, and its impact will echo for generations. Stay curious, because the next breakthrough might just rewrite reality itself.